Lecture 29, normal random variables. So you recall that Z, random variable, has a PDF, a probability density function that looks something like this. The values of random V extend from minus infinity to infinity. And so this goes on forever in this direction and in this direction. And of course, if we were to get the total area by doing a little integral calculus under this curve, we would get it to be 1, as it always must be. Okay, and I say here that we recall we've seen that a continuous random variable can have a mean and a standard deviation as well. Well, for Z, mu sub Z, we can write that like this, right? The mean of the random variable Z, not surprisingly, looking at the graph, it's 0, right? Dead center of the hump. That's actually the mean. And what is the standard deviation for Z? Well, that's not as obvious. And remember what the standard deviation is for a discrete random variable. You take each value of the random variable, subtract the mean, square it, multiply by the probability of that particular value, add them all up, and square root them. And you're getting that, when you multiply by that probability, you're getting kind of a weighting, the importance of that particular value's distance from the mean, right? Well, a lot of the values in here they're fairly close to 0, and there's where a lot of the probability is. When you get out here, the data values, they get very, very far away from 0, right? It goes for infinity in this direction and, forever in that direction as well. So there are data values way the heck out here, but the probabilities associated with values out there are so small because the curve dies off that they just don't have that much importance. And when you compute the standard deviation, again, it takes some kind of heavy calculus to get there. You actually come up with the value 1. All right, which maybe is not too surprising, but that's what we have. All right, and I say that more generally, we can talk about normal random variables with a mean mu and a standard deviation sigma. So a mean mu perhaps different from 0, a standard deviation sigma, whatever it is, perhaps different from 1. And what happens is, what we're looking at, when we talk about that, we're talking about random variables or a random variable that has probability or has values all along the real line, just like this one, but it has a different mean and a different standard deviation. It's still going to have the bell-shaped curve to its PDF, to its probability density function, but of course that hump of that bell is going to sit over wherever the mean is, and then the standard deviation is going to determine kind of how fat or fat and low or narrow and skinny the bell is. So for instance, I have just down here that I want to do like maybe 4 little kind of generic examples. So maybe I'll do it like here. So I'm in the right below below that sentence where I say more generally we can speak of a normal random variable with mean mu and standard deviation sigma. And now I want to do 4 pictures of that. So let's do one right here. Let's do mu positive. Mu can take on any value from minus infinity to infinity, depending on the kind of random variable we have. Mu positive, and let's suppose that sigma is large. All right, so what that's going to look like is, if mu is positive, it's some value out here, correct? So I'm going to hump up right here and back down. Now, if sigma is large, that's an indication that the values of the random variable tend to be spread out more. And of course, they're spread from minus infinity to infinity. But what I mean is more probability sits out there farther away from the mean. That would indicate that there's more of a weight for the values that are farther away from the mean. So you get a lower, fatter bell shape. It's still a bell shape, but it might look something like this. It might come along here, and it might go like that. Okay? And I maybe should have had it hump up just a little more or make it a little fatter, something like that. But my point is, don't necessarily compare it exactly with this one because it's its own drawing. But again, total area has to be 1. Okay, well, what if we had mu positive and sigma small? Okay, if sigma is small, I'm saying that the values of the random variable that are very, very close to mu are going to have more probability associated with them than if I had a larger standard deviation, that the values tend to be more concentrated around the mean. So again, here's the mean, mu, and this time I might make it, instead of having it start to hump up kind of early and not go too high and die down, it might actually stay very, very low until it gets real close and then die off again. Again, there's still some area. It looks like I'm touching the axis. I don't mean to be. There's still area under here going out, but it's just so tiny now, and almost all the area, almost all the probability is concentrated around mu. Not quite all of it, but almost all. But so again, total area equals 1, as before. All right, well, I guess I will go ahead and draw in, this is almost kind of silly maybe, but mu negative, sigma large. So I could have a negative mean way over here, and with a large sigma, again, I expect to see, let me see if I can draw this a little bit better here. So I want to have, my tails. Remember my tail probabilities? They're fatter. Things don't die off as fast. So, and I don't hump up as much in the middle, and I'm just spread out more, so I have a fatter tail. Okay, so again, total area equals 1. So let me say, even though maybe the drawings don't really show it, this one and this one are supposed to have fatter tails. There's more area, more probability out, and less of it right in here. And finally, we'll do a negative mu and a sigma small. Okay, and so maybe I'll put it about right here. There's my mu, and I'm still going to have that bell shape. But as before, it's going to come maybe way up like that, and then just die off real fast. Okay, so again, total area, can't stress that enough. Total area equals 1, and here we would say the tails are skinnier. Skinny, they're always skinny, but let's say skinnier. And that'd be for this one and for that one, right? Because we got more area crunched in towards the mean. Okay, next page then, I say that if x is a random variable that is normal with mean mu and standard deviation sigma, we have a way of saying that's just nice and succinct and tells all. And that is, if I want to tell you that x is, yeah, I'm still on the page, good. You can still see me. If x is normally distributed, which means it has a bell-shaped curve like that, or that, but it has mean mu and standard deviation sigma, I indicate that by saying x, and I put a little twiddle here, and then I put a big N, and then I put mu, comma, sigma in parentheses there. And the way you read that is x, we often say, is distributed as normal random variable with mean mu, standard deviation sigma. Or x has the PDF of normal random variable with mean mu and standard deviation sigma. Okay, and so what would we say about the z random variable? Remember way over here? For the z random variable, mu sub z is 0 and sigma sub z is 1. So we would say z is normally distributed with mean 0, standard deviation 1. Okay, then I have a little bit of writing here. You might want to pause me and read that paragraph. I'm going to just go through it very quickly. I mentioned that there are not many practical random experiments that have outcomes that are the standard normal random variable, z. There are not many that necessarily have as an outcome of a random experiment normal random variable with mean 0 and standard deviation 1. But I point out that in nature, and not just in nature, but in a lot of human activity, normal random variables of different means and standard deviations come up all the time. And I say here that if you think of some process that occurs in nature, or perhaps some activity that human beings do that has a random outcome, it generates values of a random variable, generates a data set. What we will find is that the random variable that's generated often is normal with some mean and some standard deviation. And I'll let you, like I said, read that paragraph on your own, but let me just give you the example then. We say here that men's heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. All right, I have just given you a statement about a population of data. If you look at all the men's heights and you measured them all and you took it all and put it in a big data set, you'd have a big population of data, and the mean of that data set would be, 69.5, and the standard deviation will be 2.4, and I say there that it's normally distributed. What that means is it's a statement about a population of data, but like I said, we can think of that population as being a huge set of data values that come from the outcome of a random experiment. And I mentioned, genetics and nutrition and all that that occur randomly across the population help to determine a person's height. So in one sense, there's the action of a random variable that's producing all this data. But in another sense, if I already have the population of data, I can think of randomly grabbing a value out of it. I can think of that as my random experiment, and that yields a random variable as well. So you can kind of think a random variable has generated the population, and you can also think the population generates values of the random variable if I draw from it randomly. We talked about this before. So when you see, my point is, the real point here then is to say that if you hear the statement, like I have here, men's heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches, that's a statement about a population of data. To do any kind of analysis on it, let's turn it into a statement about a random variable. That is, let's let m equal the height of a randomly chosen man. Okay, then what I'm saying is, I guess I've already told you there, then what we are saying, the statement that the population of data is normally distributed with mean 69.5 and standard deviation 2.4 is we're saying that this random variable, so m is now a random variable, it is distributed normally with mean 69.5 and standard deviation 2.4. Okay, that's what that means. And I say here, let's draw the PDF curve. Okay, well, let me just do it very, very roughly. It really won't be a great picture. But, way out here somewhere, I have 69.5. Okay, then if I were drawing if I took the z random variable here and just shifted it over to 69.5, I'd still have a standard deviation, a spread of 1. I want to spread it 2.4, so I got to make it a little shorter and a little fatter, right? And make the tails a little fatter. So I will draw it kind of like this, and maybe that's too much really, given the scale of the x-axis here. It's going to come in. I'm not going to fuss about this too much. It's going to come in maybe like that, all right? Because 69.5 is this far, so that's probably even like 2 spread apart, but that's all right. That's all right. So it's going to look, something like this. And again, total area is 1. Okay. And I guess I want to make a little point here, and the point is that, how do I word it? I say note that at the bottom there, note that the PDF can't possibly be exactly what we'd expect if m were perfectly normally distributed with this mean and this standard deviation. The reason for that is I've drawn the PDF to give us absurd values if it really represents the height of a man chosen at random, or the whole data set of men's heights. Because look, I'm talking about negative heights over here. Remember, this as a normal random variable, it better spread from minus infinity to infinity. So I got negative heights, or over, about here I got men who are, 10 inches tall. On this extreme, I got men who are, 50 feet tall if you go out far enough. Okay, that's ridiculous, right? So it really isn't the case that you can make the claim that M is perfectly normally distributed. In fact, what you have is that somewhere there is the shortest man in the world, and that's a cutoff, right? And somewhere there's the tallest man, or the tallest that a man could ever possibly be biologically, and so there's a cutoff. All right, so you really have kind of a truncated bell curve. But the point is, if you go down as low as you can go and still have, possible heights for men, or up as far as you can go, you get such a long interval relative to how big the standard deviation is that the tail out here is so tiny, the tail area is so tiny here and here that you can just disregard it. It'll be, 0.00000, many zeros before you get to a non-zero digit in either direction. So for practical purposes, it really is zero. So even though we technically have to truncate it, we can pretend it goes on forever with these exceedingly tiny probabilities. And that happens all the time. When we do our statistics, we are going to do all of our analysis, we're going to assume that we have normally distributed random variables, meaning values stretch from minus infinity to infinity, but in truth, probably they're truncated somewhere, but where they get truncated is such that those tail probabilities way out there are so tiny, we can just pretend they're there and just go forward with claiming we have a normal random variable. Finally, I guess I have here another example. IQs, last page, are normally distributed with mean 100, standard deviation 15. So that's saying that if I let IQ be a random variable, meaning the IQ of a person chosen at random from the population, that's saying that it's normally distributed with mean 100 and standard deviation 15. If I draw the PDF, I'm way out here, my bell will be centered at 100. It's going to look something like that, right? With a standard deviation of 15, it's got to be, it's got to have a healthy spread to it. So, however you want to draw it is like that, maybe, because it's 15 is, not a tiny standard deviation. So again, total area is 1. And again, we have that fact that, nobody can have a negative IQ. So again, we got to cut things off at both ends. But when we get out far enough, what we cut off then is so tiny that it's essentially zero, and we can just pretend it's there and pretend that we have a genuine normal curve. Okay, we'll stop here.